We now begin our study of quantum mechanics. This will be chapter 39, and this is probably the most difficult area of science that one can possibly study. It's been said by many leading physicists that no one still understands quantum theory totally. So we're on chapter 39, and the year is about the year 1900. And to give you some kind of background to begin what has happened here, we had in the past, of course, our Newton's theory of matter, and that's Newton's equations, the concept that time was invariant with everyone, and we had electromagnetic theory. The electromagnetic theory was a theory of electric and magnetic fields and of light and how light moved and so forth. So we had electric and magnetic fields and we had matter. Those were the two things. Many people thought that this was the theory of everything in 1900, and therefore nothing else would be discovered except minute things. But as we saw in our chapter on relativity, electromagnetic theory predicted that the speed of light was a constant. That is impossible and violates Newton's theory of space and time, where time is the same for everyone. And so to reconcile these, Einstein said Newton's theory of matter is incorrect and Maxwell's equations are correct, and we need another theory to replace our theory of space and time, and that was special relativity, which he did in 1905. This was followed by a theory that was able to deal with acceleration, our last chapter, and that's called the general theory of relativity. And that was done in 1916, where we learned that space and time were bent and light would be bent around matter such as a star, and our whole space and time structure was altered and bent, and that gave the illusion of gravitational forces, simply because that was the shortest line between 2 points. So all of this said electromagnetic theory is right and Newton is wrong. So now we begin to see something else happening. At the same time that Einstein's dealing with relativity, Planck came up with something in order to deal with what is called cavity radiation. Now, cavity radiation, also sometimes called blackbody radiation, is where we take an object and we bore out a cavity, and no matter what the temperature is of this object, inside this cavity there's going to be radiation. And if we make a small hole, we can look in there and let some of that radiation come out and ask what it is. Cavity radiation refers to the electromagnetic radiation inside a hole, also called blackbody radiation. It turns out it's dependent upon the temperature, but independent of the substance making the cavity. We can make this out of steel or wood or anything you could imagine. And if it's at a given temperature, the radiation in the side has the same pattern. In fact, what it will look like is it will be a curve that will peak and then go down like this, where this is the wavelength and this is the amount of the light or the intensity. So the light becomes more intense at a certain wavelength. If I make that temperature higher, then the curve shifts back over here so that I have shorter wavelengths, or I have higher frequencies, if I were to do this in terms of frequencies instead. Well, this curve right here was found to have a wavelength spectra that could not be explained by any theory. Everyone tried, and they found curves that would fit this side, curves that would fit this side, but nothing in electromagnetic theory or Newton's theory could explain why we had a particular curve that looked like this for electromagnetic radiation in a cavity. Well, what Planck did was propose something very unusual in the year 1900. You can see this is while Einstein was already working on his theory of special relativity. And Planck proposed that the walls of this cavity here were made up of oscillators, like springs with a mass on a piece of matter. and that these oscillators would oscillate, and they could only emit and absorb certain quanta of radiation. So these oscillations would have radiation that would come in, and they could only absorb certain ones and only emit certain ones. And he proposed specifically that the energy of these oscillators was equal to a number times a constant times the frequency. So this is how much energy could be emitted or absorbed. In other words, it had to be a quanta of energy, either one, this N here stands for 1, 2, 3, 4, 5, several of these bundles of pure energy that were sent out, or quanta of energy, where the frequency was multiplied by some constant. Now he planned to take that constant and let it go to zero so that you could have any possible energy and frequency that would be available. But when he actually fit these curves, he found that it would only fit for an exact constant. And that constant, h, was equal to 6.626 times 10 to the minus 34. Extremely small number, 10 to the minus 34. And it had the units of what is called action, or it would be the same as meter times momentum, which would be a kilogram meter per second squared, or it could be energy times time, either way. We'll talk about the unit for Planck's constant in a moment. And when he did that, he said, we can explain this curve if the walls are made up of oscillators and we only emit and absorb a certain quantity of radiation. How much? The energy had to be in these multiples, depending upon the frequency. So frequencies of light, if this is a given frequency, it could only emit and absorb certain energies, which are multiples of that. No one had any idea why that would be true. That finishes section 39.1, and you can see that advance was made, but we still don't have an underlying theory of why this would be correct. It makes absolutely no sense. We'll learn about that in the next section.